Okay, so the next section we're going to look at here is going to be kind of looking in terms of the impact that actually occurs when we're changing the momentum of an item. And that impact, if it's done in a very short, interval, like a lot of sporting equipment, if you would. So here we see a golf ball in contact with the head of a club. We see, we just had the example of the baseball hitting a bat. Tennis is very similar. And you're going to notice, and this is kind of cool, when you really slow these things down and you look really closely, what you end up noticing that you don't see with the naked eye in the moment is that there's deformation that's occurring. So it's pretty incredible, especially this picture. You can see that that golf ball is like there's a flat on it that is up against the club, and it is actually deforming, and it's in contact with that club head before it actually releases and goes away. So how we quantify this in our problems is we use something called the coefficient of restitution. And it is characterized as, if you would, the bounciness of different materials, and in this case, sporting equipment. So there's going to be a range. So when we have tennis balls or golf balls, there's going to be, a number that ideally, or a range of numbers ideally, that are going to be considered, acceptable for that coefficient of restitution, which is going to be how bouncy or how much this is going to deform as it's hit or moved around. So in the case of a golf ball, the coefficient of restitution is 0.83. Okay. Now we're going to be working with this in some of the problems that we're going to be looking at. Now, as we look at impact a little bit more closely, the types of impacts that we have are going to occur along what we call a line of impact. And what that means is when the center, or the center of gravity of each of the items that are having a collision, they are on that line of impact. So the center, for instance, of these two balls is along the line of impact if we would put those in direct contact. They can also have their velocities come in at a different, angle. This is called an oblique type of an impact. And that means that we're still along the line of impact with their center, but they're just coming in at different angles. Okay. What we're going to focus on is going to be the direct central impact for the problems that we're looking at. Now, the impact itself is going to be a collision between two bodies that occurs in a very small amount of time. Okay. So classics of these are going to be those sporting equipment, baseballs with bats, tennis balls with rackets, golf clubs and golf balls, that type of thing. Now, as we identified already, the line of impact is going to be the common or the normal to the surfaces as they are having the actual impact themselves. Central impact is when you have those lines of impact are in line with the actual velocities of the collision. And then you're going to notice that the oblique impact is going to be where those velocities are coming in at an angle, but the centers are still on the line of impact. Now, looking specifically at direct central impacts, like I said, are the ones that we're going to focus on in this particular section and in the problems that I have assigned for you. This is looking at two different bodies before they actually have an impact. So we have if you would, ball A going at a velocity A, and we have a ball B going at a velocity B. Based on the size of the vectors that they have shown here, velocity B is going at a slower rate than what velocity A is. So what we anticipate happening is that A is going to actually hit B, even though, B is moving as well. Now, during the point where they are in contact with one another, this is called their actual impact, and they're going to deform a little bit, okay, or a lot, depending on the type of material, and that's what kind of is going to be the driver of this coefficient of restitution. Now, as they go back to their original shape, that is when the period of restitution actually starts to happen. Okay, that's where we actually see the one bounce off of the other, if you would. But there is that little bit of deformation where they're kind of stuck together, and then as they come out of that deformation, that is where this period of restitution occurs. So as we look here, then what happens is the velocity A then transfers some of its momentum to velocity B and then, or I'm sorry, to ball B, and then it's going to be going a little bit faster. Now, to determine how fast those are going to be is going to depend on the coefficient of restitution. So if I have two, like for instance, super balls that are going to be hitting one another, we're going to notice that coefficient of restitution is going to be a very, high number. If it's going to be something that is not as bouncy or isn't going to have that bouncing effect like super balls or tennis balls, then that number is going to be smaller. Now, the largest value of the coefficient of restitution is 1, okay? So anything that is like, for instance, like that 0.8 that we saw earlier for a golf ball, we know if we drop that on the ground, a hard surface, it bounces up pretty good. So the higher the value of the coefficient of restitution, the more bouncy the actual material is in contact with the element that we have. So coefficient of restitution is going to be anywhere from 0 to 1, with 1 being like the largest number. The higher the number, the bouncier the material, if you would. Now, to calculate or the relationship of the coefficient of restitution, we're going to notice, actually, it's this equation right here. This is a little like an in-between, but here is the equation for the coefficient of restitution, with that E being the variable. So that cursive E is going to be the variable that we use here. Now, we're going to be using this equation right here in the next two sample problems that we're going to be looking at, or practice problems. So our next practice problem is actually going to be number 1318, found on page 891, and we'll do this one together. So if we go to, actually we're gonna do something beforehand. So what I want to do is, before we get to this example problem, let's pull back our equation sheet that we started for the module 5, chapter 13. The things that we looked at earlier were all from section 13.3. So now we're going to look at items from 13.4. So we're just going to add a couple more items here to this. Now, we already talked about the conservation of linear momentum, but I'm going to write it down here again because this was in conservation of linear momentum. And this is going to be when we have items that don't have an outside force acting on them. So that means that our impulse drops out. So that's going to reduce this to the momentum before, or initial, is going to be equal to the momentum after. So I just have that rewritten down here again, just so that we're going to be using it in this section. So the summation of the mass times velocities, okay, it's going to be equal to the summation of the mass times velocities after. Now, how they call out these velocities after is with a prime instead of a 1 and a 2 in this case. And it'll make more sense when we do some problems. So V is going to be the before collision, if you would, and V prime is going to be the after collision. Now, the coefficient of restitution is going to be the symbol cursive E, and E is going to be equal to velocity B prime minus velocity A prime divided by velocity A minus velocity B. The primes, again, are always the afters, and the non-primes are the befores. So when we have a collision, we are going to have two items that are going to be colliding, okay? And the A's and the B's are just calling out the different items. So when we're talking about conservation of linear momentum in regard to a collision, like the balls going together or colliding with one another, and then what is their before and after velocities, that is what they're referring to here. Okay, so this would be the A and the B velocities of two different bodies before they collide. And then the primes correspondingly are going to be the after they collide. And then that's going to equal the coefficient of restitution. So the coefficient of restitution is unitless because top and bottom, they would be, feet per second or meters per second. Okay. Now there's one other equation that I just want to add to our sheet, and it's just something that in a couple problems they ask this. So they want to know what is the energy loss that is seen, after the collision or after, an encounter or the impulse. So we would say that the change in energy, we would analyze it looking at, for instance, the kinetic energy of the before minus the kinetic energy after. Okay, you'll see that in that sample problem 13, 17 that you go through independently with the different numbers. And they ask you at the end, what is the change in the energy level? So you'll do this, but I thought it's a good place to kind of add it to our equation sheet so that we have it available. Okay. So this kind of round outs then the items from chapter 13, these two sections in the in this chapter. So now we're going to look at sample problem 1318, and it is found on page 891. Okay, zoom in here, and just a little bit. I'm going to kind of tip this so it's not so blurry. So here we have, it's a 20 megagram. So instead of a kilogram, it's a megagram. Railroad car is moving at a speed of 0.5 meters per second to the right. It collides with a 35 megagram car at rest. So they're showing that right here. So this is the 20 megagram going at a velocity of 0.5, and then it's going to collide with the second car there. After collision, the 35 megagram car moves to the right with a speed of 0.3 meters per second. Okay, 0.3 meters per second. They want us to determine the coefficient of restitution between those two cars. All right. So as we look here, variable wise, I want to kind of show you what they've got here. So on the befores, that's going to be the left-hand side here. These are before momentums. Notice that our variables are just VA and VB for our velocities. On the after side, okay, on this side over here, it's VA prime and VB prime. Those are our afters, okay? So because we are using the same bodies, A and B, before and after, the primes are added for the afters in each of these cases, okay? All right, so let's kind of put down what we know and what we need to try to find. So this is going to be sample problem 1318, okay? And this is on page 891. All right, and through the knowns and the unknowns, I'm just going to draw the diagram, okay? Because there's no need to really list the items. So I'm going to draw an A and a B equal to my A and my B, okay? This is going to be A, B, A, B, right? I know that this is 20 megagrams. This is 35 megagrams. And then on the other side, it's going to be 20 again and 35. Okay. Velocity A is equal to 0.5 meters per second. Velocity B equal to 0. This is at rest. Then we're going to have velocity A prime. We don't know what that is. Okay, that's something we're going to have to calculate. And then, but they did give us that velocity B prime was 0.3 meters per second. Okay. So now using conservation of linear momentum, so our approach going to be conservation of linear momentum, we're going to say that MA times VA plus MB times VB going to be equal to MA times VA prime plus MB times VB prime. Now, I am able to put a positive value in front of each of these because everything is going to the right. So I am simply going to add my little convention up here so that we know everything going to the right is positive. If something would be going in the opposite direction, then we would be subtracting it off, okay? Because momentum is a vector quantity. So the positive and negative is going to be direction. So now we can put in our values. Now you're going to notice here that we have megagrams for everything. Normally we are dealing with kilograms, but I'm not going to change these to kilograms because this would be 20,000, 35,000, 20,000, 35,000, and then we've got all those zeros to deal with. Because they're all megagrams, we're just going to use the 20, 35 for each one, and then they're going to cancel out anyway because we're going to be solving for velocity. If you wanted to do the kilograms, go right ahead, but I assure you we'll end up with the exact same answer. So mass for our car A, that's going to be 20, okay, times the velocity, 0.5, okay, plus we know that the velocity B is 0, so that means that this is going to go to 0. Okay, it's at rest. It does not have momentum. It will only have momentum when it's moving. Okay, it's going to be equal to the mass of A. We know that's 20. We don't know velocity A prime, so that's an unknown. Plus our mass of B, which is 35, times velocity B prime, which is 0.3. Okay, so our only unknown here is the velocity A prime. So we want to solve for that. Okay, so go ahead and solve for the velocity A prime for this equation. All right. So you're probably at about this point, you're going to notice that you end up with a negative value for VA prime. Remember, momentum is a vector. And basically, remember, we assumed we were going to the right. And if you remember back in statics, we said, well, if you end up with a negative value, that means that you didn't assume the right direction. And that is the same case here. So in this case, what that means is that it is going to the left, but we're going to leave the negative because when we use it down in the coefficient of restitution, we need to account for that negative value because it's going opposite direction of the other items. So we're going to leave it, but all this means is that it's actually going to the left instead of to the right. Okay. So any questions on that? Did everybody get 0.025? Okay. Yep. Thank you, Josh. So now the problem is asking us we wanted to find our coefficient of restitution. So our coefficient of restitution is going to be equal to, if you need to go back to your equation sheet, you can, but I'm going to write it here. Velocity V prime minus velocity A prime divided by velocity A minus velocity B. Okay. we know velocity B was 0. Okay, that was the befores. Remember the non-primes are the befores, and then the primes are the afters. So we're going to put in our velocity B prime was 0.3 minus velocity A is going to be a negative 0.025. Okay. Divided by velocity A, which was 0.5, and then minus 0. So if you do the math here, this becomes positive, okay? Our coefficient of restitution is going to be 0.65. Okay. Questions there? And that's what the question was, the problem was asking for. Okay.